Okay. Okay, so we are going to be talking about geometric mean. This is just going to help us find missing pieces in our right triangles. And we also know that triangles can be formed inside of bigger triangles, right? So we're going to talk about how those can be proportional. It's not even what's on my screen. Let's see here. Let me close that. See if that helps any. Did it change? Yes? Okay. Let's see. Let me do it on here. It works better. Okay, so in the little blank space at the top of your page right here, that's where I want you to write this information down. So we have the geometric mean is just going to be you multiplying two positive integers together, but you will put them in a proportion with x. X is basically kind of like going to be your unknown side. But these two pieces are going to be one of those triangles within a triangle. So x is going to be a side for both of your triangles, kind of like a shared side, right? Your geometric mean is going to be the square root of the product of your two numbers. So reason being, obviously, we can see that this is a proportion. On that last test we just took, we set up a whole lot of these to solve. All you did was cross multiply, and then you had to solve for x, right? Or whatever was missing. Well here, whatever a and b are, maybe they're 6 and 7. 6 times 7 would give me 42. Other direction, I have x times x. Well, what is x times x?
X squared.
X squared. And so you're going to end up with something like this, right? They had 2 over x equals x over 8. The 2 times 8 gave them 16. The x times x gave them x squared. But if I'm trying to solve for x, how do we get rid of a square? We have to take the square root. So you're going to square root both sides. The square root of 16 is 4. Okay? And that's all you have to do to find geometric mean. Whatever the two numbers are that they tell you, first one goes on top over x, second one goes on bottom under x, cross multiply and solve. Easy enough, right? Okay, so there are 3 examples on your paper. Geometric mean of 5, 20, 3, 27, 5, and 11. I want you guys to take a second, set it up just like this, and see if you can solve for x on those 3 examples on your page. Okay? So you're going to be setting up proportions on the 3 examples below. Okay, so as you guys are finishing those 3 up, they told us to find geometric mean of 2 and 8 on this example. Right, so you just took the 2 and 8 and plugged them in for a and b from the proportion given, cross multiply. 2 times 8, x times x, set it up and solve for x, right? Okay, so let's check what we should have gotten on those 3 examples. Okay, so on the first example, our numbers were 5 and 20, so we should have had 5 over x is equal to x over 20. Cross multiply, x times x is x squared. 5 times 20 is 100, right? Set it up the same way for part B. We're going to. I'm just going over proportions first. Yes, we'll solve it too. 3 and 27. 3 over x equals x over 27. Cross multiply. We got our x squared equals 81. On the last one, 5 and 11. 5 over x equals x over 11. X squared equals 55, right? Okay, so here we had to take the square root. So what did we get for our x value on that first one? 10. Good. Okay, what did we get for our x value when we took the square root of 81? Okay, on that third one, is there a square root of 55? No. So we're just going to leave it as square root of 55. That square root is not in the bottom of a fraction, so it's okay to leave the radical. Okay, so everybody kind of understand how we find geometric mean. We're good there? Okay, so next there is a theorem that we need to talk about. So this little piece that's written after it says 10-3 where it starts with the altitude, I want you to write that in this area above the two triangles right here on your paper. Okay? The altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. So that sounds a little confusing, so let's break that down. Okay, we know what an altitude is from last week. An altitude is something that comes from some vertex straight across, right? This one, it happens to be inside of the figure, but when it comes straight across, it ends up being perpendicular to whatever is across from it, right? That's where we come up with these 90-degree angles, okay? Well, before we drew this line segment right here, this was just one really big triangle, right? Like the first triangle drawn on your paper. Once I drew that line, it made the really big triangle split into two smaller triangles. So now I have this small one, this medium-sized one, and then the whole thing is still one really big triangle, right? What it's saying here is that big triangle is proportional to this one and this one, and these two are proportional to each other. Okay, if they're proportional and we know what their angles are, right? This one has a 90-degree angle, this one has a 90-degree angle, and that one had one before we cut it. They are similar triangles. Same shape, just not the same size. So that's basically what that is telling me. They're all similar triangles, okay? All right, so we are going to write down what all of that means. So this part right here, where it says altitude, it has the line AP is supposed to be under that line, but it messed up my formatting there. Okay, so you can write this kind of off to the side over by the smaller triangle on your paper. But we had this really big triangle, DAB. That's what they're saying that this one right here is representing. Right? The first one that's drawn on mine. You do not have to draw these three triangles. Just copy down what pops up. Okay, so this one is representing DAB, the really big one. This middle one is representing that triangle that is formed right here, okay? EAB. Okay, this one right here is representing this small one over here on the side, EDA. So once they're all taken apart and all turned the same way, we can see they're the exact same triangle, right? Just made smaller and smaller, even though it doesn't necessarily look like that when they're all turned different directions, okay? So all of these have a 90-degree angle, this one at point A, these ones at E, right? Meaning they all have a hypotenuse, which also means they all have a short leg and a long leg, right? So whenever we set up proportions to find missing sides, we can say that the hypotenuses are corresponding, the short legs, the long legs, whatever it is we need to set up, okay? So they're basically just saying the really big one is similar to the middle-sized one, right? Triangle ADB is similar to EAB. And the big one is also similar to the little bitty one. And that the medium-sized one and the small one also similar. So all three of these end up being similar triangles. Okay? All right, everybody get all that part over there before I cover the next slide. So they also have a little summary written there at the bottom of our page saying that the geometric mean you find by taking the square root of whatever the numbers are that you multiply together, and that the altitude can form three right triangles that should all be similar. All right, once you've got that down, you can flip it over onto the back. I'll have to change the slide. Not yet. All right, that's the part we already copied down, right? We already talked about that. Oh, wait. Did I go too far? No, you already copied this down, didn't you? Okay, all right, just making sure. All right. Okay, this is where we are now. So you flip it over onto the back, and we have corollary 1. A corollary is just like a theorem, just a different name for it. It's usually like a piece of a theorem, so it's not like the full-blown idea, just a piece of it that you can use to help you do whatever you're trying to set up at the time, a small rule that allows you to set something up. So you're going to copy this little piece down at the top of the page right over here. So it says that a corollary for the heartbeat is when the altitude is drawn to the hypotenuse. So it comes from the right angle directly across the big triangle. And the length of that altitude, the line that you draw in here, you can find it using the geometric mean, the process we just learned on the front page. So A over X equals X over B can help you find the length of this line. Okay. And it's saying that your A and B would just be segments from your triangle. So it could be segment AN, this little piece right here, the bottom, over this piece that we're saying is X, or the geometric mean, is equal to X, or the geometric mean, over in B, this piece, right, that it was corresponding in the bottom. Okay, so given triangle ABC, the whole thing, that has some right angle, then your altitude will be CN, which just means you can find it using that formula we learned on the front, geometric mean. Okay. All right, does everybody have this part up here written down? That's the important part that you have for this. Yeah. Okay. You good there? Still confident? Okay. All right, so where does it get the term heartbeat? Well, if you've seen the heartbeat on a monitor, right, it's some straight line that goes up, back down, straight line, up, down, and it repeats that pattern, right? It's saying that's what's formed in your figure whenever you use this formula. So we said it would be AN, which would be this piece, and then you would go up for this line, right? AN over CN, or NC, is equal to NC. So you're going to come back down that line over the straight line. Okay, so if you're using this formula, think of it as looking like a heartbeat. Okay, it'll be this piece over this piece, you go up, is equal to, go back down, that same piece over the straight line. Okay, so it's kind of just a little picture to help you remember what your proportion should look like. Does that make sense? This over this equals this over this. So just go in the order of your heartbeat. Okay. Oh, sorry. Okay. So then there is one with numbers on it drawn in this box on your page. So we are going to use this to set up and solve for x. Okay, so if we follow the heartbeat, that should be what number is going to go on top? 4 over, and then you come back down is equal to over, there we go. Okay. So this is what you will use when looking for your altitude inside of a figure. Okay? And then we would just cross multiply and solve just like we did on the front page. So 4 times 25 and x times x. So we would end up with x squared equals 100. Take your square root. What must x be? There we go. Make sense? Okay. Everybody have that before I change it? All right. Ignore that. Okay. This is, again, just splitting it into those pieces. Okay. On to corollary 2. So again, this is just another idea that we use to help us find missing pieces. So this one says, and again, this is what you're going to write in the top of that little section above your 3 triangles. It says when the altitude is drawn to the hypotenuse of a right triangle, each leg is the geometric mean. So instead of the altitude being your geometric mean, or x, it's saying the legs are now your geometric mean. So that would be this side and this side, right? Okay. So this is what you're going to say is your x now, or this is what you're going to say is your x now. Okay. So given that you have this really big triangle, ABC, angle C was 90 degrees, and you had an altitude coming across, forming these 2 right angles down here, as long as you've got this picture, then your altitude is still the CN, but now these are going to be my unknowns. So it depends on which side you're wanting to find. If you want to find this one over here, then we'll use this proportion. Okay? And it says BA, which is the entire bottom, right, over AC, so this is our x this time, is equal to AC, the one we said was x, over AN, the tiny piece. Okay? So entire bottom over the side, come back down, smaller piece on the bottom. Okay? So BA over AC is equal to AC over AN. So bottom over side equals side over smaller bottom piece. Okay? Same thing works if you wanted to find side BC over here. Okay? So you'd have BA, the entire bottom, is equal to over BC is equal to BC over the smaller piece from the bottom. So doesn't matter which side you want to use, you do the entire bottom over your side is equal to side over the smaller piece from the bottom. And just depends on which side you want to find. Okay, so let's look at some examples for that. Okay, so we have this given here. We know this is what we're going to be setting up, right? BA, the whole bottom, over AC, that side, is equal to AC or CA, whatever you want to call it, over the small piece from the bottom. Okay? Or, other way around. The entire bottom over the leg you're looking for is equal to the leg you're looking for over that same smaller piece but from the bottom. Okay? All right. So, let's do those examples that they have drawn out here. Okay? So, on this one we're solving for x. So, this is our unknown side, right? Okay? So, I'm going to go the whole bottom goes on top, right? The entire thing. So, what would I put right here? Over my side is equal to my side over the smaller piece from the bottom, which would be 4, right? Okay. Then we would just cross multiply and solve like usual. So 29 times 4 is 116. X times x is x squared. There is no perfect square root of 116, so we're just going to leave it as x equals square root of 116. Okay? So again, whole bottom over the leg we're looking for is equal to the leg we're looking for over the small piece from the bottom. Okay? So everybody understood where these came from in the proportion? Okay. All right. Let's do another example where we're looking for the other leg. Okay? So now this is the side I'm looking for. Okay? I'm going to do the entire bottom over that side is equal to that side over the smaller portion from the bottom. Okay? So what goes on top of this fraction and what goes on the bottom of this one? Perfect. And again, we just cross multiply and solve. Okay? And again, no perfect squares. We just leave it as our radical over there. Alright. So, also I think it has this written at the bottom of y'all's paper too. It says, when looking for an altitude, so when you're looking to find this line, so when this line is your x, you're going to use the heartbeat method. Okay? If you're looking for one of these outside legs, that's when you use the rounding method. Okay? Alright, and that is all. Let me stop the video.